And one more thing. Doug Cutting might have been working with Hadoop for 10 years. He's been 8. So almost as long as Doug Cutting.
Yeah, so to get started with, I'm Sreekanth. So as Doug started working in 2006, I joined Yahoo in 2007, 2008. I worked in the Hadoop team. I was working with the MapReduce framework. So quite a lot of things which you guys blame today might have been me. And so that's my thing. So I currently work with Lazada, where I work under John for the data engineering team. Our responsibilities include operationalizing data. So we are pretty big in terms of the amount of data which we pull. We pull in around like 1 to 2 terabytes of data a day. And our Kafka clusters generate around 1.5 terabytes of data a day. So we have still not reached our full potential. I would say we are around 5%. And on our peak day, we have capacity to grow 20 times more. And that's the scale which we are planning to grow also for a period of time. So that's just about me. So even though I'm presenting here, most of the knowledge is not just me. So this is, as Doug said, you just jump into the fire and learn to battle it. So when I joined Lazada, we had just started out with Kafka. So before this, none of us had any Kafka experience. We just had an AWS instance with 3 nodes and a documentation saying that this is how you do it. Well, that's how we started. And so I saw quite a lot of guys raising their hands for Apache Kafka. I believe lots of you guys know about Kafka, but this is just a brief 5-minute overview about what Kafka is. So Kafka is high throughput, low latency, distributed commit log. That's it. It's high throughput, low latency, distributed commit log, which is rethought as a publish-subscribe model. So lots of Java programmers know something about JMS and all the messaging systems from the past, like RabbitMQ, but Kafka is not that. Even though it supports publish-subscribe, it's not a JMS-compliant message queue. It's a distributed commit log. What does it guarantee? So it guarantees you orders by nature of it being a commit log. So data which is committed is never lost until you decide that, hey, I don't want to read data older than 5 days old. Yep, that's happened. So, and it's consistent. It's fairly consistent. It's reliable, fairly, because of the distributed nature of it. And it's a publish-subscribe messaging system. So that essentially means that you publish, you don't care about who is subscribing it, and subscribers don't care about how the data lands up into it. So it fairly decouples. Quite a lot of use cases for Kafka is that you use it as a buffer to absorb the data flow, because you can have a publisher who's producing quite a lot of data and subscribers can't subscribe it as fast as it is, or consumers who can consume pretty fast, and as a publisher you don't have to care about it. So that's where the PubSub model helps, but you don't have really things like notification or guaranteed delivery. So the maximum Kafka can give you is at least once semantics, but then that's configurable up to you. So when we talk about it, so there are a few components in a Kafka system. One is a broker. So broker is something which we'll talk about. Then there are topics. Topics are something similar to a messaging system. So you have a topic to which you publish, to a topic to which you subscribe. The messages come to you. You don't have to worry about anything. Then there are publishers and subscribers. It's a traditional producer-consumer problem in computing systems, wherein you have something which keeps producing data and something which consumes data. And Kafka just makes it handle as a distributed system. It has fairly reliable way of evenly distributing load. So that's a brief about Kafka. Now, if I'm going too fast, let me know. We can talk about it at the end. So what is Kafka at Lazada right now? So we have 9 brokers. We currently clock around 698 million events a day. And this is 2 weeks ago, before we onboarded 2 systems. And we have 100 plus publishers who publish data to us. We have 20 plus subscribers. Our primary use cases are clickstream and log aggregation. And we handle up to 1.5 terabytes of data. And this is somewhere around
1.5 terabytes of data in total?
In a day.
A day?
Yeah, in a day.
Okay, right.
Yeah, so in a day. And this is not even up to 10% of the machine utilization. So, and I believe we have enough. So this is on an average day. On a peak day, it is 20 times more. So, and we still have spare capacity on top of it. So that's the kind of things which we do. And so this is our typical Kafka cluster wherein you have a producer who's producing to a broker and a broker B. And since I said it's a fairly consistent system, so you have a ZOOKEEPER who keeps the quorum for you. So it essentially says that everything, you have a fairly consistent view about the system. That's what ZOOKEEPER helps you. And you have multiple consumers. So you can have consumers consuming data from one broker, multiple consumers consuming from the same broker. So it's essentially decoupled. So the data generation and data consumption are totally decoupled. And you don't have to worry about it. And there is ZOOKEEPER who would take care of the consistent view of the system. So that's how a typical traditional producer-consumer in a Kafka system works. Like this is very, very, very high level. So this is just to say that, okay, this is all fluff. And so let's get into how we started handling fire. So we have a situation. We have one full disk on one broker. Okay, 100%. So it's gone. So we don't know why it happened.
Can you go back to the last slide? In MapReduce framework, we know which key, which mapper output will go to which producer. Here, what is the policy? As best, what is the policy?
So, okay, so to be honest, there is also a key notion and a key partitioning notion, but it is not traditional MapReduce. And the reason being is that in a traditional MapReduce, you are more worried about splits, saying that how much data should go to a mapper, and then you control the reducer, which you can have different partitioning strategies. Here, it's pretty simple. You just have a key and a value, and your partitioning is based on key. It is just a hash partition. Whereas in MapReduce, you can have total order partitioner, you can have custom partitioners, which do so many other things. But this is just assume it to be a bucketing. So it's basically a consistent hashing system. So situation one is that the broker is down. So we'll get into details on each of it. One disk is full, but there are other 3 disks on the system which have less than 5% usage. So why? I mean, the root cause is imbalanced partition. So now this leads to a question on what the hell is a partition in a Kafka system. So when I talked about initially, when I briefly glimpsed about saying that Kafka is nothing but a distributed commit log, rethought as a publish-subscribe model, this is how a partition internally looks like. You have a topic. A topic has multiple partitions, and each partition has a segment. So in a traditional write-ahead log, you write each commits, and each commits get organized into a segment. Multiple segments get organized into a topic, into a partition, and multiple partition gets organized into a topic. So in essence, what Kafka does is handles all the synchronization problems as a segment. So it's a queue at segment level. So what happens is that when a producer is reading, it reads from the head of the queue. So queue is first in, first out. So it will go from the tail. It will keep moving. Producer will just keep adding into the head. So that's how it works. So now you can see that you have partitions, you have segments, you have a topic. So this doesn't still answer our question that why did one disk get full? So this talks about what a partition is. This says that every partition determines how many reads and how many writes can happen in parallel. If you create more consumers than the maximum number of partitions, extra ones don't get anything. So you'll have to be really careful about how many partitions you want, because in one end, you have too few a partition, then you don't have too many. You can't make use of parallelism. Everything goes to the single guy. If you have too many, then you have an extra overhead. You have overhead on maintenance data. It has to be, you are creating so many files on the file system. It is going to get split across multiple disks, which is a good thing. But you're talking about the other things and the other thing to be noticed is that the partition resides on a single disk, and it can't spill across disks. So this answers our question that even though we had 3 disks which were empty, less than 5%, we had one partition which was imbalanced compared to n number of topics which we were running in the cluster. And this goes back into the way Kafka assigns things for you. So Kafka assigns disks based on the disk which has the least partition. It doesn't care about how much data a partition contains. So you can as well as lead with 2 heavy hitting partitions on the same disk, and remaining all partitions which have low volume of data get assigned to various other places. So there are multiple ways of fixing this. One is that you move your partition, which is not very intuitive. But one thing which I'll tell you is that when you are planning out a cluster, the very first thing you need to know about when you're doing Kafka is plan the partitions, number of partitions, because you want to know how many people can read from it, because that's very important in a streaming workflow, because you want to process the data as fast as you come. So you can't have more than a second or a 2 delay in streaming workflow. And the number of disks, because finally how much data you can consume in a day is dependent on how much disk you have. So if you have pretty large capacity in disk, well, fine, you have great. But if you have smaller disks, as we do currently, so you will have to now have a calculation saying that, okay, each partition gets so much data, so how many topics can I have with the current disk which I have? Because you don't want your disk to go beyond 70 to 80%, because the moment the failure happens, you would have to replicate all these data across. So that's the thing. Yeah.
Now that you mentioned that the hash based partitioning all the data gets into one single bucket.
Yeah.
Any other automated system?
So I have not looked into the API, but it makes sense that there would be a way that you can do that. But so typically what we do is from our use case, we don't need, why would you want to partition your data based on a key? The reason why you want to partition based on C is that some set of keys end up to same set of guys. This is traditionally in case of you have an ordered data and you want to maintain an order within that. Typically we don't have that use case, but then yes, it is possible that all the data can land up in a single partition. That essentially means that you would have to generate your key on which you are partitioning as wide as possible. Now, if your key generation is bad, it's traditional K value store problem, wherein you're going to have hotspots. So yeah, it can cause problems, but you can override it. You'll have to take a look at the API. But till now, we don't have a use case where we need that, because we don't have an implicit order which we require. And so that is to do with partition. So the whole idea is that this we learned in a very hard way, wherein disk got full, 2 heavy hitting partitions landed up on the same disk, and we didn't notice until it was 100%, and that typically happens on a Saturday 2 a.m. and you get an alert. Cluster is down. So at 2 a.m. you have to figure out what the hell happened, and this is what actually happened. So
excuse me. You say on the last line, plan this well ahead. What do you mean by well ahead? How well ahead?
So in the sense that if you have a large disk, 4 terabyte disk, you have 4 terabyte disks, so you have 16 terabytes on a machine. You're pretty much safe. But if you have like 200 GB, you can't go about importing, I'll support 100 topics, because you don't have the space to store. Huh?
You don't know when is the explosion. And also,
yeah, so
capacity to be too big, whereby, what happens if it's under capacity? I mean, there's a balance you keep, but how do you reach this optimum value?
So the way we reach the optimum value is we see how much data will be generated in a day, and we plan for a downtime of 24 hours. Things can go wrong. People don't come back in 24 hours. So we keep at least 48 hours of data in ourselves and plan for 20% more on a peak day. That gives us a number which we want to target, and then we see how much we can do. So at the worst case, we'll just export the data, put it on an S3 bucket, and then load it back. But this is primarily that you have an existing hardware and you want to run a Kafka on it, which is our use case. We have ordered our hardware, but this is what we have currently. So which essentially means that when we talk to people who want to publish to Kafka, we have to make a plan. Say that this is the spare capacity which we have, this is the downtime which we can take, so this is how you have to do it. So this is something which leads towards an operationalizing thing, which is something which we have to do because we grew explosively in a month's time. In a month, 10 times data started flowing in, and things happen. And when things like this happen, that's when you might have thought you are safe, but this is where it will bite you. And as usual, it's always on the weekend. So now comes to another question, that the same situation again. Broker is down, the entire cluster is down rather. Whenever we restart, brokers just get stuck. We don't know why. And we see lots of failures to ZOOKEEPER. Again, we don't know why. And if you look at it, we're seeing 400 plus K connections to ZOOKEEPER. Now, the only reason you would see so many connections is when it's a DDoS. Why would you don't have 400K publishers, so why would you do that? So the only clue which we got was that all of these are Fluentd. So if people who do log aggregation would know that what Fluentd is your log aggregation stack. So it's all in Fluentd, but then this all means to that connection, there is a connection leak in Fluentd, but we don't know why. Why is this happening? Because Fluentd is a pretty mature stack. So because we were working with Fluentd for quite some time. Again, on a Saturday morning, same thing happens. You're woken up, and you don't know why it happened. So we went and diagnosed it, and we figured out that the root cause was that Kafka has something by enabled, which is auto topic creation. We disabled it. And the reason why we disabled it is because this leads back to the previous thing, where as a user, you don't get to choose which disk the partition gets to be placed on. Since we don't want random people to connect and create partitions and create topics, we disabled it. So what led to this? This led to us to discover something else which not many people talk about. ZOOKEEPER is currently like de facto standard in most of the organization, but nobody talks about why it's important in a Kafka system. ZOOKEEPER in a Kafka system maintains the list of brokers. It maintains a list of topics. It maintains a list of replicas of a topic. It says how far a consumer has consumed the data. You have to protect it. And you have to clean up the ZOOKEEPER data periodically. Let's be honest. If the ZOOKEEPER has an issue, your cluster is down. And so what was actually happening with Fluentd is that it was trying to look up a topic in the ZOOKEEPER. It was not able to find up the ZOOKEEPER topic. And then it tries to write it to ZOOKEEPER, and it's not allowed to do that. So it fails. It goes back. So we end up having quite a lot of failed connections on the ZOOKEEPER end, which essentially means none of our brokers could do any work. And this just says that this is how ZOOKEEPER is, that if you start running a cluster with Kafka, the most important part in your cluster is maintaining the ZOOKEEPER quorum and make sure that it is always consistent. The moment the consistency is lost in the ZOOKEEPER, things go wrong. And by things go wrong, it means it goes really bad. That you are talking about huge data loss and maybe reset of the cluster. So take special care on ZOOKEEPER. There are quite a lot of documentations on saying that how you should manage a ZOOKEEPER cluster, how you should do it. And the other thing to note is that the ZOOKEEPER has transaction logs. Clean it up periodically. This can get pretty huge. This points back to a number of partitions. So the data on ZOOKEEPER is proportional to that. So you'll have to plan your partitions, have maintenance on the ZOOKEEPER transaction logs so that your cluster is healthy, because you don't want 100% on the ZOOKEEPER data disks also.
Did you evaluate MongoDB with respect to why it's
No, we don't use MongoDB at all.
there also did you write
No, so it's not related to this. So ZOOKEEPER is used for coordination, distributed coordination, and people implement distributed locking with that, but that's not what ZOOKEEPER is meant to do. So you can do it, but nobody stop it. I mean, it's not what it's meant to do. So situation C is things are working fine, but we have leaderless partition. So when we say that there are leaderless partitions in Kafka, that essentially means, as I said, you lose one end of the parallelism. So you can't do that many reads and that many writes, and some consumers are not getting any data. That essentially means you're wasting resources. So why? Again, so when you say leaderless partitions, that means some data in the ZOOKEEPER is broken. You don't know what's broken. You don't know how it's broken. So we went and figured out by spending quite a lot of time that we had an inconsistency in our configuration, that some nodes had an unclean leader election being enabled, and some didn't have. And there is a history behind it also, and the reason is that this gets back to our functioning behind what a broker is. So broker is responsible for managing all the list of partitions. It sends ACKs back to the message, which says producer don't need to resend data. It commits a message. This is when the consumer can start reading the data from that place. It replicates the data, and it also gives you durability guarantee. So whenever you talk about a distributed system, you are talking about some kind of barrier. So broker introduced that barrier to you, which says that a data which is ACKed, a message which is ACKed need not be resent. And a data which is committed can now be read, and there is no further changes onto it. Now, this is what is the functionality of a broker, along with it replicating the data. And in a typical cluster wherein you want a higher durability guarantee, you need to look at two things, which is the number of replicas which you want to be in sync with the leader, and how many ACKs you need from it. So traditionally what an ACK says is that if a broker who is a leader accepts it, that's fine, that's an ACK. But when you say an ACK of -1, it says that you and your in-sync replica should have it. So when you say the minimum number of replicas 2, -1, and 3, that's the strongest guarantee you can have in a Kafka system. That essentially means a message which is ACKed is always there for you till you read it, or you never read it and it's just expired. So the thing which you have to plan based on your message requirement is how durable should your message be. And there are various states of data loss in a Kafka system, which I am not going to go into because traditional distributed systems, it's very difficult to know it until you know all the failure scenarios. In this case, traditionally, if you want a data which is very critical that a producer gets an ACK back, is never lost, set minimum in-sync replica to 2 and replication factor to 3, and set required ACK as -1, and this should handle most of your use cases. Now the only reason you want to play with this is that it's okay to lose the data, but in some cases, clickstream, it's okay to lose non-important events, but in case of data like financial data, you don't want that to happen. So this also brings to another thing is what is fault tolerance in Kafka. So Kafka has a leader and a follower pattern. It's something similar to a master. There is a leader who has the most updated copy. The followers pull the data from him. This is the responsibility of a controller, which runs within a broker. Now, this data is stored in ZOOKEEPER. So that's where how things are in ZOOKEEPER is important comes into picture. And it also has a maintenance count of number of in-sync replicas, which determine how much replicas do you need per partition, the minimum number of in-sync replicas per partition. This gives you durability guarantees of your machine. And Darren brings in our thing about unclean leader election. So it's a cluster. You are running more than one machine. Things go wrong. Things fail. Sometimes node goes down forever. So if Kafka has a setting wherein it disables unclean leader election and especially in a situation wherein you just need the cluster to be available, you enable it. We had serious hardware faults for which we had to enable it, and it just happened that we enabled it only on 2 nodes, and we are somehow able to scrunch up and get the cluster running. We forgot to change it back. So this over a period of time cost us to have partitions with leader as -1 because there were conflicting views on offsets on what each one saw. And whenever there's a conflict, what happens in case of Kafka is that the partition is marked leaderless. That means no data can flow through it. The only way you can work around is that add new partitions. So the key thing here is that there is no magic bullet for how do you do your Kafka cluster. Ideally, you partition your Kafka clusters into multiple ones depending on how important a data is, and set different message durability patterns. And the other thing to be noted is that even though there is a notion of in-sync replica, Kafka still allows you to lag behind. So if you have an offset of 100, something can be 90 and still be in sync. So there are multiple knobs, especially in terms of consistency, which is something which you have to be very careful in terms of a distributed system, is that what is consistent is dependent on how you configure the system. In this case, we did something to bring our system back up for higher availability, which caused inconsistency. So play with the unclean leader election if you want to do higher availability with data loss. So in our case, we lost around 1% data, but that's because we were able to bring it up on time. So be very careful about this, because it's very easy to change it to bring a broker back up. So if you can get your hardware back up in like 30 minutes, well, fine. But if it takes more time, then it becomes a problem. And then there is also something like a control shutdown, which enables you to gracefully do a rolling upgrade on a Kafka cluster. So this is another thing which is by default enabled, but then there are configuration knobs you might want to do it, because sometimes replicas can go out of sync and it might take time to replicate, your network is slow and things like that. So other thing to be noted that is here. So
can I ask a question? What kind of data were you losing this one?
clickstream, impressions. That's okay. We are not an ad company, so that's. What?
Is there any restriction on the message size being transferred?
So there is size restriction, I believe, around 2 GB or something, but that's typically you don't want to transfer binary blobs on Kafka. Nobody's stopping you, but there are better ways to do it. So this is a current ongoing investigation. This is what is happening currently. That this is something which you're observing right now. We are still debugging. We have potential leads, but we don't know what's happening here. So the typical symptom is that one broker goes down and producers start slowing down. So this essentially means we are looking at 1 to 2 messages in a minute compared to 100K to 200K messages in a minute. So potential leads are that we have a discovery loop in Kafka and IO module, which is causing CPU spikes. The reason being is that what happens in case of a broker down is that Kafka producer's buffer gets full, and when it gets full, there's a configuration which says that block till you are able to flush the message. And there is an NIO cycle wherein you wake up all your sockets to do a select poll. And then that causes a CPU cycle, because that's one symptom which we see. We have seen CPU, but not many messages going through. Other thing which we're looking at is, again, Fluentd, which is one of a stack. It does a round robin, so which essentially says that it initially sees 5 brokers, and then now suddenly one has gone down, so it goes and blocks on the 4th one and waits forever. That could be a reason. So one way is to restart the Fluentd and see if things work, but in some cases it works, some cases it doesn't work. And some case we found that migrating replicas to a different broker compared to what was on the previous one helps, but again, it still doesn't answer the question that why does it in the first place exist. We are still looking at it. Only 2 leads are this, and this is how we fix it. We fix it by migrating the replica, and things work. or restart the producer. But this is something which you'll have to watch out when you're kind of deploying it and doing it. So other thing which I want to stress about is that something which people have to do is Kafka has a notion called consumer groups. What consumer groups is that it's a bunch of consumers with a single group ID. So what this gives you is it parallelizes the reads across the multiple JVMs. So if you have consumers belonging to simple consumer groups, the data is parallelized across all JVMs. And when a consumer goes offline, the data is rebalanced automatically for you. So this gives you a better elasticity in terms of your consumers can go down. You can do a rolling upgrades on data which you're reading it. So, and other things which you need to know is that consumers have auto commit. So what I mean by auto commit is that once a consumer reads a message, every 100 milliseconds or 1 second, the offset is committed. So if you want real transactional semantics, make sure that you read, do your full commit, and then commit the ID, because that's the best way to look at it. And the data for this is maintained in ZOOKEEPER. So most of our deployment is in 0.8 in Kafka. In 0.9, this data is partially moved out from ZOOKEEPER. So this essentially says that if you flush your ZOOKEEPER data, then the consumer are going to see the duplicate data. So do enable char auto enable commit, because by default it is true. You don't want it true in case of transactional systems, because you can lose data, which you do it. So if you want at least once, just make sure that, sorry, not at least, exactly once. This is one of the semantics, one of the configuration ops you have to take care of. And things of metrics which you have to watch out for is number of unreplicated partition. This points to something is wrong with your network or your broker. Leader election rate. This essentially points that something is going on between your brokers. Maybe they are not able to talk to each other. CPU cycles. It should be 0. Ideally, it should be 0. But we don't live in an ideal world. And record send rate on producer, because you don't want stuck producers. So you're allowed to monitor that, especially in case of one broker going down. You want to make sure that this is pretty consistent and you don't see a pretty drastic drop. And finally, I want to talk about the hardware considerations which you should do on broker is that you don't need any RAID on broker. So don't invest on hardware which has RAID control or hardware RAID control not required. Kafka is not CPU bound, so you don't need pretty beefy systems for this. No SSDs. It's a commit log, so it writes sequentially. So spinning disks are better. Buy more spinning disks. Don't spend on SSDs. You need SSD for ZOOKEEPER data because it's quorum. You probably want to build a SSD-based ZOOKEEPER data. And if you want high throughput, really high throughput, you would have to tune your PDF flush, which is basically your page cache size settings in Linux kernel. So you can just look at your VM dirty ratio, which essentially says that how much data you can write in memory. So the way Kafka works is that it writes into page cache, and it relies on OS to flush the data onto the disk. So you want a really, really high throughput. This is something which you want to do, and you want to play around with your RAM settings so that run a broker on a single box with just 8 and have a really, really high value of the VM dirty ratio. And the way it handles failure is that there is always an in-sync replica. So there is always this data on somebody else's page cache. So you can probably read from there so you don't lose data. And you rely on our operating system to do it. So you can look at different file systems which interact really well with page caching. So, but we have not reached a stage where we have to start tuning our file system for better optimized page cache reads and writes. But this is something which we do about, tune about the VM dirty cache, because we want to do high throughput. If you're talking about streaming workflows with a second latency, this is something which you want to do with Kafka and add more replication. That's it. So it's cheaper to hit the neighbor's RAM than hit your disk. So that's it. So that's all I have for today's talk, and it's pretty short. So any questions? Yeah.
For the SSD, right? do you have any benchmark? So what's the failure rates that you have?
So
Because
that's
you used to have like you write once and you read many times, right? But looks like you are writing so many times and you're reading.
no. So we don't use SSDs for Kafka brokers. Kafka brokers is for spinning disks, with normal hard disks.
Your ZOOKEEPER data.
ZOOKEEPER data, you want pretty much fast writes. So I frankly speaking, I'm not much of failure rates in SSDs. There are other better people than me here in that. So, but it's traditionally it's recommended that you maintain ZOOKEEPER data in SSDs because, and the other thing is that ZOOKEEPER also has a notion of quorum. So even if you lose one node, you still have a quorum. It's fine. So, and the quorum is replicated on the disk, so you probably want to do that. You do want better performance in that case. Yes. Yeah.
You mentioned that SSD for Kafka and not SSD for Kafka doesn't need SSD and ZOOKEEPER needs SSD, right? Does it mean that you're running the ZOOKEEPER forum away from the
Yeah.
Kafka?
So the reason why Kafka doesn't need an SSD is sequential writes and sequential reads. So that's not an SSD's use case. And the reason for SSD for ZOOKEEPER is it has to be fast. It has to be fast because every offset commit is on ZOOKEEPER. And quite a lot of operations go on ZOOKEEPER. So quite a lot of consistency operations go on to ZOOKEEPER, that's why. Anything else?
So other than the 9 brokers that you run, so you also have a ZOOKEEPER forum, which is how many?
So we have 5.
5
Yeah. 5 nodes in an ensemble, yeah. So, yes.
What is your retention period for this 1.5 terabyte?
So each one has different use case. So for some topics we have 3 to 4 days retention. In some case we have less than 6 hours because we have workflows which pulls the data out. So when I say 1.5 terabytes, we consume out pretty fast, like really fast. So we don't have to worry about it.
So the majority of the data that you're looking at is effectively traffic through the site, how people are interacting with the site, what they're clicking through.
Yeah.
You're losing, if you lose the 1%, are you allowed to tell me what you're...
No, my boss will fire me. So we have other use cases also, but it's much easier to say clickstream, and it's something which most of the organizations use Kafka for. So that's something which we do.
Okay.
We ship logs also.
Yeah, it's nothing so you can do. Clickstream, logs, just general logs from around the company.
Other thing to be noted is that decoupled systems. You want to build a decoupled system. And that's traditional use case for messaging system. So you have a system which produces quite a lot of messages, and your end stream consumers can't do it. So you probably would want to look into that. It acts as a good buffer for you. Yeah.
Yeah, so one of the things, I'm just going to jump in for a second. One of the reasons we use Kafka is, you just touched on the subject, is it kind of decouples us from the rest of the company. So the data comes in, we've got one consistent interface, which is the Kafka REST API. And, yeah.
Yeah, so.
2, I don't know, correct me if I'm wrong. And a number of different systems can write to that. Okay, and then when we pull the data off, so like for log transports, we keep copies of the logs for us for long-term analysis by us and also perhaps by the engineering infra team, but it also might be split and go to Elasticsearch where the infra team or engineering team can keep track of things that's happening right now, look for spikes or downtime and things like that. So we've got one source coming in, it's a consistent interface, and then a bunch of different systems can actually consume that data. And we don't have to worry about it, we just tell people that it's available. Okay? And if they have the rights, then they can consume it.
So that's where it acts as a big buffer to you. So.
I'll have to do some more reading on Kafka. Thank you.
Yeah. Yes.
Did you face
any type synchronization problems?
So that's, we run on the same clock, so we don't have to worry about it. But Kafka's notion is not dependent on time. It's kind of an internalized vector clock with an offset. That's all. Offset. It's just an offset to broker.
Not even for ZOOKEEPER?
No. We run as I said, we run a clock. I have not seen us lag behind. So it typically happens when you have a little large cluster and different things. We don't have that time synchronization issues.
Everything is on a single rack?
Not on a single rack, it's split across, but still it's pretty consistent. I mean, we might have few nanoseconds lag, but that's pretty okay in typical traditional systems.
Can I ask you what flavor of Linux are you running this on?
So we run it on CentOS 7. So only few things we have done in tuning parameters is dirty ratio, number of sockets. That is just to standard scaling about 500K. That's it.
You mentioned earlier that if the requirements, or later on if you realize that you need to tune stuff like the file system, have you ever considered tuning kernel stuff?
We can, but at this point of time, we don't have time for it. So if we have tuning on kernel and file system for Kafka, then maybe that's a good talk for the next thing. Maybe in a year's time, you have reached that stage. So
What do you plan to do for, earlier you had said you have some ongoing issues in the earlier slide.
Yeah.
What do you do for observation and monitoring?
So we have a separate system for it. It uses YAML, so you can emit it to ganglia, and from ganglia. So we monitor these things, unreplicated replicas, leader election rate, and record sent on producer. This is our alerting. So standard monitoring stack, ganglia, and run alerting on ganglia metrics. But that's what we do. This is enough, most probably.
So if you had to diagnose you had a slide earlier with this. I'm sorry. This one. So how would you actually go about diagnosing this? Do you read all the source?
Lots of JStack, and lots of digging around the code. That's it. So this has happened many times. Stack trace, 100, 200, 300 stack trace. And end of the day, we still have not figured out. So still going on. Because it's kind of a very corner case which we hit. Maybe it's an environmental thing. Lots of things can play into it, especially in something distributed. So that's why we are not sure, but for most of the other things we are sure pretty much what's the reason. So
Okay, one more question in the back, and then.
Yeah.
Sorry to be the annoying one. Who are your customers? The consumers here? Are you cycling the streaming data into an ML platform? Because what are you doing with it?
So that's, again, so we have multiple consumers, quite a lot of consumers. But then I don't know, I don't want to disclose things but we have to say, yeah, we have ML use cases also. And streaming ML use cases also. So that's all. But I can't disclose beyond that.
And it's not that secretive. But, yeah. So a lot of the consumers are just writing into data pipelines.
Yeah. So one of the easiest consumers is data pipelines. So we build out early Hive tables out of this. We do have streaming use cases. But yeah, it's slowly coming up.
Right. The reason why I was asking that is Spark has the streaming ML.
So that brings into our things which stack and all stuff. So it's something which we want to look into, but at this point of time, we don't have a driving need, maybe in a quarter's time. But again, two good things about Hadoop. One good thing about Hadoop is it's very fast moving. Two is that lots of projects don't have a great shelf life. So before we jump into something, we need to know about it, because we don't want to end up doing something and then redo everything later 3 months down the line, because it's huge technical debt. So we are just being very cautious in that area. So we adopt what is mature.
Okay.
Sure.
Sreekanth, thank you very much.
Thanks, Chris. Thanks. I still have a job, right?